Hello dear students, today in this video we are going to talk about a very important topic from the solid state physics. The topic title is band theory of solids. I know most of the students get very confused in dealing with this particular topic. Once I talk about band theory of solids, what comes into your mind of average students? They think that there is a valence band, there is some conduction band. For metals or conductor, the valence band and conduction band supermerge, and for semiconductor the valence bands and conduction bands are far are away, maybe of the order of 1 electron volt gap between them, and for insulator the gap between the valence band and conduction band is more than 6 electron volt. That's it. But many of the students get confused with how exactly these bands are formed. Today in this lecture I will try to explain the whole concept in a very precise manner, and I hope after attending this lecture you will have no confusion on this topic. So without any further ado, let's start. The topic name is, and let's give today's date, it is 21st of July 2024, and the topic of today's discussion is band theory of solids. This is a very interesting topic actually. When you talk about the band theory of solids, there may be two approaches to explain this band theory of solid. One approach is very simple, very trivial approach. The first approach, maybe you can think of like solids consist of atoms. Now atoms, individual atoms have their own energy level, and once you once you take them or bring them closer, the energy levels gets overlapped and it forms the bands. Actually, the valence band wave functions, the valence electron wave function gets superimposed on each other when we take the atoms closer to each other, and they form bands. So let's take an example. This is the first approach. It's a very trivial approach. Our main approach will be the second approach, which we will talk about. Okay, before explaining this, let me just briefly specify what is the second approach. In the second approach, we will consider the periodicity of the lattice, how the periodic structure of the lattice potential gives rise to energy bands. Okay, so first talk about this first one. So this is very simple. If you have an individual atom, they will have their atomic level. Okay, and let's say this is energy versus this is the internuclear distance. Okay, so energy versus the internuclear distance. Now once you see the internuclear distance is large, individual atoms are there, their energy levels will not superimpose on each other. Now as you are decreasing the internuclear distance, you are coming towards the left. What will happen? As you decrease the internuclear distance, this level gets splitted. Okay, so this is we have drawn for one atom. Let's say we take an example of sodium solid. Okay, solid sodium. So this is for one. This is a pair of sodium atoms. Okay, now if there are more number of sodium atoms, let's say 5 sodium atoms, what will happen? There, as long as they are wide apart, you will get a single atomic level. As you reduce the distance between the individual atoms, their atomic level will start interfering with each other, and let's say instead of 2 sodium atoms, if you have let's say 5 sodium atoms, this will be like this. Now in actual solid there are a lot of sodium atoms, so what will happen? This will make a continuous band. Understand? For an example, if you are considering sodium, so 11 Na, what is the electronic configuration? It is 1s2, 2s2, 2p6, 1s2, 2s2, 2p6, 3s1. So this is the valence electron. Now if you consider one sodium atom, it has one valence electron, and corresponding to that you will get one valence wave function, let's say. Okay. Now as long as the sodium atoms are very far away from each other, you will get a single line, because the valence electron wave functions are not superimposing on each other. And as you keep on reducing the internuclear distance, let's say this is for one sodium atoms, this is for another sodium atoms, this is for another sodium atom. So on reducing the internuclear distance, this forms a complete band. Okay. So let's say you are plotting for this is 2p. Okay. Again for 3s, one sodium atom will have 3s, this 3s, this 3s, this 3s, for another. The problems comes, I should not call it a problem. This event occurs when you reduce the distance. What will happen? Again, so you can see these are the region which are allowed, and there is a gap between the next allowed region, and thus you can explain like this one is the allowed band and this is the forbidden band. Okay. Now what happens in case of this kind of metal? These two bands overlap, and for the semiconductor they are distance, they are separated by some distance. Okay, we have let's say I am drawing it for carbon or silicon. Okay, I am showing both carbon and silicon the same graph. For carbon we have 1s2, 2s2, 2p2. For silicon it is neon, then you will have 3s2, 3p2. So if you consider the valence electrons, they are on the 2s and 2p. Okay. So let's say this is 2s and this is 2p. Let's say this is the drawing for one carbon atom. Okay. So energy versus internuclear distance. This is for one carbon atom. As long as the carbon atoms, individual carbon atoms, isolated carbon atoms are there, you will get only these two lines. Now in solid, you know, atoms are not far away from each other, they are very closely spaced. Okay. For sodium it is around 0.376 nanometer. So you can see the order. So obviously the internuclear distance is around this. So what happens? Let me just quickly confirm it. Okay. So what happens? First, you see, you are reducing the internuclear distance. You are taking the atoms closer to each other. So first, these two atomic levels will superimpose. Okay. Then again, if you further reduce the internuclear distance, then these two bands will get separated. As you can see, these are the allowed region, these are all allowed region, this is the forbidden region. So this is like, if you consider like this. Okay. So for carbon, you see, this is the maximum valence band and this is the minimum conduction band. This is your conduction band, this is your valence band, and the gap between them is the energy gap. It is around 6 electron volt for carbon, and as you can see, this is the allowed band, then this is the conduction band, this is the valence band, and this is the forbidden gap. I hope you are getting my point. And this is the case of carbon. For silicon, you have you see, this is 3s and 3p. So if this is 3s and 3p, the basic structure will be same, but here the silicon has lower band gap. It's around 1.1 electron volt. So I'm just writing for the time being, it is 1 electron volt, 1.1 electron volt. Okay. So this is how bands are formed. So this is a very qualitative explanation of how bands are formed. Now what you will be doing will be taking up the second approach, which is more of quantitative in nature. Okay, we can solve Schrodinger equation, we can use mathematical equations to explain how this bands, allowed bands and forbidden bands arise. Okay, so let's start. The second approach. Look, this first approach is quite handy. You can easily understand how bands are formed. Let's talk about the second approach. To understand this second approach, band theory of solids, we have to look inside the metal. Okay, band theory of solids came later, but before that some preliminary model came. One is nearly free electron model or free electron model. It's a classical model. You must be heard of this free electron model. So a scientist in 19th century, I guess, whose name was Drude, he postulated that inside the metal, metal consists of tremendous amount of electrons, right? So he considered that, Drude considered that inside the metal, the electrons are completely free to move. Okay, and no electron is belonging to a particular ion. The electrons are free to move inside the conductor or metal. Okay, so what he assumed, that look, there are positive ions. These are positive ions, and these electrons are not localized, they are delocalized. Okay, so these positive ions will give rise to potential. Drude assumed that the potential offered by these positive atoms are constant potential, is a constant potential. And considering this constant potential, this scientist Drude was able to explain various phenomena or various properties of solids, and this includes, the first one is it proves the validity of Ohm's law. Ohm's law, V is equals to IR, means if you apply some potential V between 2 points, you get current I, and R is there. R is the resistance coming from this interaction of these electrons with these ions. What Drude missed, he ignored the interaction between these electrons. Okay, so using Drude model, various properties got explained. As one thing I told you, that it validates Ohm's law. This model perfectly, this model also explained thermal conductivity and electrical conductivity. In fact, there is a law. Okay, let me just check it. Yes, there is a law that the ratio of thermal conductivity and electrical conductivity is constant. Okay, that is given by Weidmann-Franz law. And other thing it explained. Later, Lorentz did some modification to this theory of Drude. He considered this electron as electron gas, and he said that these electrons follow Maxwell-Boltzmann statistics. So Lorentz incorporated the idea that these electrons follow this classical statistics called Maxwell-Boltzmann statistics. Okay, now this model was successful in explaining various phenomena, and I would like to mention two particular limitations of this free electron model, and this is classical model, free electron gas model. Considering these electrons are free electron gas, the name free electron gas model is basically a classical model. And taking this classical model, what problem was arose? Okay, the first problem which arose at that time was the electronic specific heat. If we consider the electronic energy, let's say this is 3 by 2 nkt. If we consider only the translational degrees of freedom for the electron, we have 3 by 2 nkt, and from this you can calculate the specific heat. This is 3 by 2 R, universal gas constant. But actually, what we know, this is not correct. So this classical model predicts that 50% of the contribution of the specific heat comes from the electrons only, 3 by 2 R, but actually experimentally what do you know, it is the specific heat is 3 R. Here we are getting 3 by 2 R. What does it mean? 50% of the contribution is coming from the electron only. This is not correct. So this is one limitation which was there in the classical theory of free electron gas. And second one is this paramagnetic susceptibility. As per this model, paramagnetic susceptibility was given to be proportional to 1 by T. But you know, this paramagnetic susceptibility is independent of the temperature. So these two things was not getting explained by using the classical free electron theory. Later, Sommerfeld, you must be knowing this name, Sommerfeld introduced the quantum theory. He postulated that these free electron gas, they do not follow the classical Maxwell-Boltzmann statistics, rather they follow the Fermi-Dirac statistics. So once you incorporate the quantum idea, Fermi-Dirac statistics, then what will happen? These two discrepancies will be got resolved. Let me show you how these two discrepancies got resolved. So what Sommerfeld did, he postulated that these electrons are following the Fermi-Dirac statistics. Now if I consider the energy levels like this, if you consider them to fermion, there is a limit, electrons being spin half particle. So in one energy level there can be 2s plus 1 means 2 electrons. Okay, so electrons gets filled up, okay, like this 2 electrons in a particular state, and it will be filled up to this level. Let's call this quantum number to be NF, and the maximum energy of the highest occupied electron is EF, the Fermi energy. Now as per this Sommerfeld theory, not 50% of the electrons, not the specific heat contribution coming from the electron is not 50%, rather it's less than 1%. As per this theory, the electrons which are lying in the range of kT, only those electrons contribute to the electronic specific heat. Okay, and the precise number of electrons which contribute to the electronic specific heat is given by n times kT by EF. Every quantity is carrying the usual meaning, or this is written as n times T upon Tf. This Tf is called the Fermi temperature, and as you can see, this Tf is nothing but EF by KB. Okay. So how the discrepancies are removed? Previously we got the electronic specific heat contribution. We have got it is 3 by 2 R, but after incorporating, so you see 3 by 2 N KB or 3 by 2 R. This was the result from the classical statistics. Now from the quantum statistics, this N will be replaced by this thing. Okay. Now after following the Fermi, this is according to the Maxwell-Boltzmann statistics. Once you incorporate the Fermi-Dirac statistics, this N will be replaced by this. So your CV will be approximately 3 by 2 N KB T by TF. We are putting this N is replaced by N into T by TF, and as you can see, it is proportional to T, and you already know the electronic specific contribution is proportional to T, and it becomes 0 as you go to T tends to 0. The electronic contribution of to the specific it will become 0, and at the high temperature, you know, the specific it becomes 3R. So using incorporating this quantum statistics, that discrepancy is removed. Now the second discrepancy was about the paramagnetic susceptibility. It was proportional to 1 by T. Now if you multiply this factor, chi was proportional to 1 by T. Now if you multiply this factor of KT by TF, KT by EF, okay, so you can see this T get cancelled, so it becomes a constant, which is the experimental result. So these two discrepancies were removed when you consider the Fermi-Dirac statistics. Now let me just summarize the whole thing which I have talked till now. Firstly, free electron gas theory came with Drude. He postulated the constant potential experienced by the electron. Then Lorentz incorporated the other thing, that same thing actually he modified, he upgraded the thing which was given by Drude. He introduced that the electrons follow Maxwell-Boltzmann statistics, and combiningly these two things were termed as Lorentz-Drude model. Now this classical model failed to explain these two things, and Sommerfeld then introduced the idea, quantum mechanical idea, and he explained those discrepancies. So till now this is fine. But even after incorporating this Fermi-Dirac distribution, few things could not be explained. Like few solids behaves as conductor, few solids behaves as semiconductor, few solids behave as insulators. Why? Their origin could not be explained by using the classical or quantum mechanical free electron theory, and for that reason band theory of solids come into existence. Now we will start the band theory of solids by understanding what went wrong in this free electron theory. So what went wrong was the oversimplification of the crystal potential. What was the problem? Oversimplification of the crystal potential. Crystal potential, here is the potential offered by the ions primarily. Now let me tell you why this is the problem. As I told you, inside the crystal we have the positive ions, and in the free electron theory the electrons were considered to be delocalized, but let's assume we have one electron here, one positive ion, let's say one electron. Now if I consider this particular electron, what kind of contribution it can have? Potential energy may come from various things. This is the main contribution coming from this ion. This ion can also contribute, this electron can also contribute. and moreover these ions are not completely at rest, they are vibrating, so that contribution should also be taken care. Okay, so you can see the actual potential has these many stories. So the actual potential will be quite complicated, very complicated. So what we have to do? We have to make some assumption. So the first assumption we made that these positive ions, they are treated to be at rest. They are considered to be at rest, and this electron interaction, that interaction is taken as constant. Okay. So these assumptions or these modifications were done on the free electron gas theory, and because of this we get the idea of bands, which were not which we could not explain using the free electron gas theory. Okay, so let me just show you. Let's take the very simple case of one dimensional array of atoms. Okay, so atoms are there like this, actually positive ions, one dimensional array of ions, and we are plotting the potential V of x is there versus x. So what kind of potential they create at the place of the ions? Potential will be more like this, potential will be minimal actually, no? So this kind of potential, and if I want to show the surface, you can show it like this. This denotes surface. So higher potential means the electrons cannot come out of the cannot come out of the surface. Okay. So this kind of potential profile we get, but do you think you can solve this kind of potential? It is very complicated potential. I think you have not seen this kind of potential in quantum mechanics. So what you need, we need to simplify. So a model is there called Kronig-Penney model. Kronig-Penney model gives you a reasonable approximation of this potential which I have just taught. Kronig-Penney model. So this Kronig-Penney model simplifies this potential, and using this model we will be able to explain. And as you can see, one thing I missed, the very important thing, that this potential is periodic in nature. As I told you, what was the assumption? The ions were assumed to be rest, and the resultant potential is considered to be periodic in nature. So with some distance the potential is repeated. Okay. So Kronig-Penney model deals with the one kind of periodic potential, which is the simplified version of this actual potential. So this kind of potential you have seen before also. So electron is moving in this kind of potential. You can see what is the period then? A plus B. The one dimensional array of ions we consider, you can see this is the lattice spacing, let us say A. Okay, and this period is A plus B. Okay, let me just check it. Now for this case it is A plus B. Minus B to 0, 0 to A, the total is, this length is A, this length is B, with actually the period is A plus B. Now this is a periodic potential. Now for this kind of periodic potential we need to know a theorem that is called Bloch theorem. Now if you have, let's say, just give me a second. Okay, for the constant potential, what do you get for the Schrodinger equation? D square psi by dx square plus twice m by h cut square E minus V naught into psi is equal to 0. You get this one, and for this V0 is a constant potential. For this constant potential you get a solution like this, e to the power as a plus minus I k x. When you replace this constant potential by a periodic potential, as this is a periodic potential V of x with a period A plus B, okay, so you can write V of x is equals to V of x plus A plus B. So for this kind of periodic potential, V of x with period, let's say A, so V of x plus A is equals to Vx. In general, I am talking about the Bloch theorem. The solution of the Schrodinger equation gets modified by some multiplication factor. Okay, that factor has the periodicity of the lattice. Okay, so the modified solution of the Schrodinger equation becomes e to the power plus minus I k x and some multiplication factor of u k of x. This u k of x has the period of the lattice, means u k at x plus A will be u k of x, where A is the lattice parameter. Okay, so whenever we get a periodic potential, we can directly assume this solution. We can directly assume this solution psi of x e to the power plus minus I k x u k x. This is known as the Bloch theorem. So this is a Bloch function. Okay. Now let's incorporate this idea into this Kronig model. So we can see there are two regions. One is between minus b less than x less than a. This is one region. Here you can see the potential. It has some finite potential, let's say V naught, and in between 0 to a it is 0. So two regions. In the first region, let us write, okay, let's write this region first, then we will talk about this region, because here the potential is 0, so it is easy to handle. 0 less than x less than a. So here what we will get, d square psi by dx square plus twice m by h cut square. What was that? E psi is equals to 0. Okay, and we wrote it as d square psi by dx square plus, let's write it alpha square. So the solution psi of x is equals to, okay, let's keep it like this. Alpha here root over twice m e by h cut square, or alpha square is equals to twice m e by h cut square. This is a very important parameter, alpha square, and you can see this alpha square is proportional to the energy. So whenever you see alpha, you can correlate with energy. For this region minus b less than x less than 0, for this region what we'll have? We'll have d square psi by dx square plus twice m by h cut square. Here we have e minus v naught, let's say psi is equals to 0, this height is V naught, okay, and this is written as d square psi by dx square plus beta square psi is equals to 0, and here beta is, you can see, root over twice m e minus v naught by h cut square, right? So beta square is twice m e minus v naught by h cut square. Now to solve these Schrodinger equations, what help you can take? You can take help of the Bloch theorem. You know the potential is periodic, so we can directly assume the solution in this form: e to the power plus minus ikx, the plane wave solution, modulated by this Bloch function ukx. Okay. So for this model, what you can write? The solution, I am just omitting, I hope you have understood this one. Kronig model we are discussing. Okay. So you will assume the solution of the Schrodinger equation to be psi of x equals to e to the power ikx ukx, and for this present case, this ukx has the periodicity of the crystal, so you can write ukx is ukx plus a plus b. Now by taking this psi, you can put it into the Schrodinger equation, which we got two Schrodinger equations, one involving alpha, another involving beta. So you can take this psi x and put them. So after that you will have a huge calculation, and after doing those calculations you will end up getting an expression. I am just writing that expression because if I start deriving everything, then this thing will be very long, really very long. So you will get an expression like this in terms of our known parameters: beta square, why my pen is not accompanying me, beta square plus alpha square divided by 2 alpha beta sine hyperbolic beta b sine alpha a plus cos hyperbolic beta b cos alpha a, this is equals to cos k a plus b. So you will end up getting this equation. Now Kronig considered some approximation. He considered that this V naught is infinitely high and the width b is negligibly small. So what you can expect? Previously, if this was the picture, this was minus b, this was 0 to a. So if you make this V naught infinitely high, b very small, this will converted into this Dirac delta functions, right, separated by the distance of a, and V naught into b in the limit V naught tends to infinity, b tends to 0, this should give you a finite quantity. So he considered this approximation. Then what he gets, let's do that, and as you can see, if we incorporate these quantities, then what will be the value of sine hyperbolic beta b? If you consider beta equals to 0, sine hyperbolic beta b will be approximately equals to beta b, and cos hyperbolic beta b will be approximately 1 if you made beta tends to 0. Okay, then if you incorporate these things here, what ultimate expression you get? And furthermore, we can calculate this beta square plus alpha square by 2 alpha beta value, beta square plus alpha square by 2 alpha beta. What is the value of this thing? Look, beta square is twice m by h cut square e minus v naught, and in alpha square we have only v naught, right, divided by 2 alpha beta. This v naught get cancelled. So what you get? We are getting m v naught, sorry, e minus v naught. Here you have, okay, sorry, v naught minus e, na, v naught minus e plus e. We made some mistake in defining beta. Okay, you can correct it. Beta is equals to twice m by h cut square root v naught minus e. Okay, just correct it. So you get m v naught divided by alpha beta h cut square. Now incorporate all these things. Sin hyperbolic beta b is equals to beta b. Then cos hyperbolic beta b is 1, and this beta is 0, so it becomes cos ka. So let's see what you get. Beta square plus alpha square by 2 alpha beta. This will be m v naught by alpha beta h cut square. This is beta b sin alpha a will remain as it is, plus this is 1 cos alpha a, this is cos k. Okay, now you can see this beta and beta is getting cancelled. Sin alpha is there. If there is alpha, so if we want to make it alpha a, we have to multiply a, right, m v naught a by, let's say, h cut square sin alpha a by alpha a plus cos alpha a, this is equals to cos k. I think the ink gets dried. Okay, so let's keep this alpha here, m v naught a by alpha h cut square. Oh, have we made any mistake? Acha, not m v naught. Okay, b was there now. M v naught b by alpha beta h cut square. So m v naught b by alpha h cut square. Okay, sin alpha a plus cos alpha equals to cos k. So this parameter m v naught, here you see alpha a is there, here is alpha a is there, here is alpha. So if I multiply a and divide a, then we can define a quantity, let's say p. P is equals to m v naught b a divided by h cut square. If we consider this particular quantity has a great significance. It contains the term v naught into b. Okay, that is called barrier strength. This v naught into b is called barrier strength. It shows this value of p shows how tightly the electrons are bound to the ions. That is why it has great importance. You see, if we make this thing narrower, it means the electron will be tighter. Okay, instead of this, if you make this, the electron will be more tightly bound. So this represents that thing. Okay, now how? Let me just read it. P has the physical meaning of binding an electron more strongly to a particular potential L, and it is clear. As the well get narrower, it means it is getting more tightly bound. So let's use this value of P, m v naught ba by h cut square. So we have taken a, so we have to divide by a. So alpha a will be there. Okay, so let's write it here. I need a bigger board. So P, in P we have taken an extra a and we had sin alpha a and alpha was there, so we have to divide by a. So P into sin alpha a by alpha a plus cos alpha a, this is equals to cos k a. This is a very important equation. If you solve this equation, we have to solve it graphically. How graphically we solve equations? Let's say you are given this equation, you have to plot the function on the left hand side and you have to plot the function on the right hand side, and the intersection will give you the solution. That is how graphical methods work. So if I plot the left hand side, what kind of plot you will get, and after this you will understand the origin of bands. But the ink of my pen is almost empty. Okay, but I want to make it a one-cut video. Anyways, okay. It will be uniform on both sides, but pardon me for my drawing. Okay. So we are plotting against alpha a, and this function is being plotted along the y-axis. On the right hand side, you see it should be equals to cos k a. Now the problem with this function, or the fun with this function, is it is restricted between two values, plus 1 and minus 1. So only those values will be allowed which will lie between plus 1 and minus 1. Okay, I should have drawn it. Okay, let's say this is the origin is here, this is minus 1 and this is plus 1. Let's say this is your plus 1, this is your minus 1. Okay, the cos function can be between plus 1 and minus 1, means the values which are more than plus 1, like this, you can see these regions, these regions, these regions, which are beyond plus 1, they are not allowed. Okay, let's first write it. This is 0. Okay, okay, let's draw it where they are cutting like this. It should not cross plus minus 1. That is what we have to keep in mind. So these solid lines are those regions which are allowed, and the broken lines are those regions where the value is either it is more than minus 1 or more than plus 1. Those are forbidden region. So allowed region are this. So if I call it, this is pi, this is 2 pi, 3 pi, and so on. So you can see this region here, the energy values are allowed. Similarly, this region is allowed region, this region is allowed region, but this region between them is forbidden. Okay, so this is the forbidden gap. forbidden band, you can say, and this for allowed band. And we have drawn it for a typical value of P 3 pi by 2. Depending on the value of P, we get different kind of band structure. Let me explain by taking different values of P. Okay, and here we have plotted alpha A means, and as I have shown you, alpha is a function of energy. So alpha means energy. You are going along this direction means you are increasing the energy. Okay, as you go right side, your allowed energy range, allowed energy band will be larger and the forbidden energy band will be smaller or decreasing. Now this is a typical moderate value, P equals to 3 pi by 2. Now we can take two extreme conditions, P can be 0 and P can be infinity, and let's see what kind of structure you get. Okay, let's say we make P tends to 0. Okay, let me just check it once. If we are considering total 3 cases, one case I have already discussed, which is the general case. The two extreme case, one is, let's say P tends to infinity. So V naught B is finite quantity, V naught is infinity. This is the actual case actually. What do you expect here? The potential steps are like Dirac delta function, you know. So if P is infinity, P sin alpha by alpha A, this should be a finite quantity, right? So when this is possible, if you make P tends to infinity, then your sin alpha A must be 0. This is the only possibility. This is equals to sin n pi. So what is alpha? Alpha is n pi by A, and we further know alpha square is equals to twice m E by h cut square, or from here you get E is equals to alpha square h cut square by twice m. And what is alpha? Alpha is n pi by A, so this is n square pi square h cut square by twice m a square. I think this is very familiar to you. This is the case of particle in a box problem, where we have seen this discrete energies. Okay, so on this extreme range P tends to infinity, we no longer get a band, we get discrete energies. Okay, separated by these energy intervals. So this is the case when you consider P tends to infinity. P tends to infinity means what? P is depending on V naught B, means you are making this V naught tending to infinity. Potential is infinity means the electrons are very tightly bound to the positive ions. Now let's take another extreme case, P tending to 0. So if you make P tending to 0, then what you will have? You will have cos alpha A. P tending to the first term will vanish, cos alpha A is equals to cos K. So what is the value of alpha? Alpha is equals to K. So if alpha is equals to K, alpha square E is equals to alpha square h cut square by 2m, means here we get E is equals to h cut square K square by 2m. And you know it. What is this energy expression? This energy expression we get in case of a free particle. And you know, for free particle, all the energy values are allowed. K is continuous, energy is continuous. What do you mean? Get a continuous energies like this. Considering P tends to infinity, we get discrete energy levels. When you consider P tends to 0, we get continuous energy levels. And when we take the intermediate case, P is equals to less 3 pi by 2, we got bands separated by some forbidden gap. Okay, so let me summarize all these things. So it all depends upon how you assume the potential. In the free electron gas theory, where we consider the potential to be a constant potential or even a zero potential, we get continuum of energies. So this is I am just showing you, this is a continuum of energy. My pen is betraying me today. So this is the energy band you get, continuous energy band you get when you consider zero potential or constant potential. This is free particle, right? Now when you consider P is equals to 3 pi by 2 as in the Kronig model, okay, in this case it's all depend upon the value of P, means the value of V naught actually. Note, you get bands like this separated by some forbidden gap. This is allowed band, this is the forbidden band, okay. Now the other extreme case, here you have taken P tends to 0, sorry, P is equals to 3 pi by 2, let's say. And when you take P tends to infinity, you got this scenario like this, okay. Instead of a band, you get lines. So this is the whole picture. I hope you understood this thing. And this particular thing is known as, this is given in tight binding model. Tight binding model. In tight binding model, the electrons are not delocalized. They are assigned to a particular ion strongly. They do not generally hop around, okay. They can move to the neighboring atom, but the chance is very less. So for tight binding model, you get the usual picture of this discrete energy levels, okay. So I hope in this one lecture you have understood the band theory of solids. My pen, if my pen is not betraying, one last thing I would like to told you about the Brillouin zones, okay. If I consider the dispersion relation, energy versus momentum, EK diagram, can I get an alternative pen? Just give me a second. If you try to understand the band formation with the help of EK diagram, we can do it in this way. The pen is still not right. So for free electron, you know how does the EK diagram look? It's parabolic in nature, like this. Okay, this is not looking like exactly parabola. Now, this is the case of a free particle. Now, when you consider the electron to be inside the crystal, so here we have the relation E equals to h square k square by 2m. But you know, when the electrons are moving inside the crystal, instead of this mass, normal mass, we have to consider the effective mass. Okay, then we can apply all the classical laws. And once you incorporate this effective mass, there is a slight change. Okay, let me just draw it here. Energy versus K. So I am just drawing with a dotted line. This was the free electron, when the electron is not experiencing any potential. Now when we keep the electron inside the crystal, we have to consider the effective mass, and the energy band diagram also change. So it is no longer parabolic, but it will be like this, it will open up. Okay, for the very low K values it will be parabolic, but as you reach to the value of minus pi by a plus pi by a, it will give you the point of inflection called. So this region minus pi by a to plus pi by, this is one of the first Brillouin zone. Okay, and you can see at this values plus minus pi by a, we get two values of E. From here another band starts, minus 2 pi by a plus 2 pi by a. So this region is the allowed region, then these values are not allowed. So this is the allowed band, these are the allowed bands, and this is the forbidden band, and it will be like this. So this is a beautiful picture, and in this way you can understand the band formation. I hope this lecture will help you a lot. If you have any query, question, you can let me know in the comment section. There are a lot of things to say, but I may have missed something maybe, but I have given the overall idea. If you still have further questions regarding this band formation and all, you can let me know in the comment section. I will definitely try to help you out. Thank you.